Okay, we're ready to get started again. Do you have the meeting number? You need the meeting ID. So we're going to begin today by talking about the different rainfall types that you can set up in Geisha. And so there are 4 different kinds of rainfall you can define for a Geisha model. You can define either a uniform rainfall, and that's basically a uniform precipitation, precipitation intensity for your model. This is number 20A lesson. And you can also define gauge precipitation, which is just rain gauges. You can define a hyetograph, which is a graph of precipitation versus time. And then you can use radar rainfall data, which is just gridded rainfall information. And so if you use uniform precipitation, you define your intensity and your rainfall duration. Your intensity is defined in millimeters per hour and duration in minutes. There's an option also to use a hyetograph, which is a graph of precipitation versus time. And for this method, you just define a rainfall distribution as well as a total storm depth. So here's the distribution. You define a distribution as well as a depth. You can also use rain gauges, and to do rain gauges you define a rain gauge coverage. And in the rain gauge coverage, so you have something like this. Geisha has 2 options for using rain gauges. The first option uses Thiessen polygons, and you define your rain gauge locations. The other option uses something called IDW interpolation, which is inverse distance weighted. And so you can use either option. If you use Thiessen polygons, then Geisha determines the Thiessen polygons for your rain gauges and uses that. If you use IDW, it uses this inverse distance weighted interpolation method to get your precipitation values for each cell in your watershed.
Do we need to do any steps to consider the rain gauges, like in week 1? Remember that we need to recalculate the basin parameter to use the weight for each gauge.
Yeah, so if you don't have to recompute the basin parameters, because when WMS saves the Geisha file, it will save the locations of the rain gauges. Then Geisha figures out what precipitation values to assign to each grid cell based on what you select. So if you select IDW, it assigns the precipitation values based on the IDW interpolation. If you use Thiessen polygons, it just uses the Thiessen polygons. So Geisha, so you don't have to recompute anything. You just resave your file if you make changes.
For HEC 1, we need to repeat?
For HEC 1, yes, you would need to recompute your basin data if you make changes to your gauges. Or for HMS. So HEC 1 or HMS, you need to recompute your basin data if you make changes to your gauges. But for Geisha, you do not. So another option that is available is you can use NexRad, well, just radar data. So if you have a time series of grids, if you have several grids, and we looked at this yesterday, you can read in the grids, and then WMS will create rain gauges so you select this option, you read in your grid files, and usually you'll have more than one grid because there's more than one precipitation time step, and then WMS will create these rain gauges for each of the cells on your rainfall grid. So this is if you have radar data. And each of these rain gauges has a rainfall distribution that was defined from your gridded data. So another option in WMS is when you create when you create this rainfall data, there's an option right here to create a 2D grid rainfall data set, so you can view the rainfall. You can view an animation of your rainfall in WMS, and so this is the rainfall displayed in WMS, so you can visualize your rainfall data. And also you can export that animation to Google Earth. I guess I don't have the animation here, so I can't show you the animation, but anyway, you can export it to Google Earth and view the rainfall animation in Google Earth along with your water depths in your watershed. So I've already shown you how to, yesterday I showed you how to use the radar rainfall data, and we've kind of talked about the different precipitation options a little bit. I just wanted to talk about that a little more, talk about all the options. The other thing I want to talk about is long-term simulation. So this is lesson 20B. And so long-term simulations are simulations that include more than just one storm event, so more than a single event. That's a long-term simulation. And there are several additional parameters that you need to define if you're doing a long-term simulation. And WMS only uses certain formats WMS and Geisha actually only accept long-term data files for long-term simulations in certain formats. And you can define your precipitation using hyetograph. So you just read your hyetograph into the XY series editor. So if we go back here to WMS, I'll wait for this to finish. I got a password, so I don't. Thank you though. So I can go back here to WMS, and if I read in a Geisha project, so I'll read in a Geisha project. You can define your precipitation data just using either gauge data, or you can define a hyetograph. So you can use the same precipitation value for your whole watershed, and you can just define your precipitation here. So that's not a problem. You just copy and paste from Excel your precipitation data for the long-term simulation. Another way there are some other parameters, some additional parameters that you have to define though. So for a long-term simulation, you have to define something called HMET data, which stands for hydrometeorological data. And that data has to be defined from the time before your precipitation starts until after your precipitation ends. So you have to have HMET data, and we'll talk about what that is. But the HMET data has to be formatted in a format that Geisha can handle. and that includes evapotranspiration parameters for your watershed. And you also want to define some evapotranspiration. The method that's used, that we recommend using, is this Penman method. And you'll want to turn that on if you're doing a long-term simulation. You also have to turn on this option to run the long-term simulation. So right here there's a long-term simulation option. It's kind of hard to see on the screen, but there's this option, and then you define your long-term simulation parameters in this window. So your HMET file is defined right here in this part of the window. So these are some parameters. These are evapotranspiration parameters, and you just create a new mapping table with your evapotranspiration parameters and define those parameters. So there's a program called the time series editor, and let me show you the time series editor. It's installed when you install WMS. This is the time series editor. The time series editor can be used to import and convert time series data, and I can open, if I have time series data in several formats, there's a way to open the time series data into this program. And there are several formats that it supports. If you have just a text file with time series data in any format, you could read that file in. Let me just show you how that's done. So here I have some long-term data, and so this is an HMET file. This has hydrometeorological data. If I wanted to read this data into the time series editor and view the data, I can just open this file. And we could read this HMET text file in, and it comes into this import file wizard. And so for this file, it has the year. So this column is the year, month, day, and then this is hour, and then this value. So then there are different hydrometeorological data values here, and I can't remember what all these are. I think this is the temperature. Maybe this is the temperature. Anyway, so you go here and you select the next button, and then you define this is the year, month, day, this is hour, and then you define data values. So this is a value, and you define the units. So maybe this is degrees C, and maybe this is, so we'll call this temperature, call it temp. And anyway, there are other values, and I can't remember what each of these columns are, but you would know, if you have the data, you'd know the different values. Maybe one of these values is like the wind speed. So column 8, we can just define this as a value, and this is km per hour. So this is wind speed, something like that. Anyway, you could read this data in, And then there's an option to convert this to a format to an HMET file. So you can save it as an HMET file that you can read into Geisha. Let's just save this. Call it time series 1.hmet. And then when you do that, you map your make sure your values are mapped correctly. So wind speed is mapped to the wind speed, temperature, and then so probably all the other values are these other HMET file values that are required. Anyway, I can go in and read all this in, save this out. And normally, so I would save that out, and I would go ahead and read that into Geisha. So this is just used for reading and converting time series data in different formats. Yeah.
In this situation, all pixels have the same values.
What has the same value?
All pixels in the Geisha. The Geisha pixels. All grade will take the same value.
Okay.
Because
Yeah.
you give values for each parameter, temperature, wind speed.
Yeah. So if you do this, then all the pixels have the same value. So do you want different values for each pixel?
There's a different value.
So there's a way to do that. If you have, so here's my Geisha simulation. If I wanted to do a long-term simulation with different values for each pixel, you would go to this long-term simulation window, and then you can define raster HMET files. And so this option lets you read in ArcInfo ASCII grid, so you have different values for each pixel. But you would have to create those grids yourself, and you can do that in WMS, but there's not a really easy way of doing it. You just have to have ArcInfo ASCII grids for each time step in your simulation. You would define your starting date for the grids, your ending date, and then you define something called a catalog file. The format of this file is on the Geisha Wiki website. So you'd have to go to the Geisha Wiki website, and then you would define the folder that contains all of your gridded data. So there's not a way in WMS to create these files, but you can manually set up different values for each grid cell. Otherwise, you just use the same value, same HMET values for each grid cell.
And for HMET files, even if I would like to connect with ArcGIS, this is only for evaluation creation, you mean, or for any time series I can. And yesterday you showed us how to import rainfall data, like time series of rainfall with grid data. Right?
Yeah.
So in this case, all the parameters that I will create through ArcGIS or whatever will contain the evaluation creation values, or will be the temperature, wind speed, the other parameters, and will be computed the ET within them.
So it's you define your temperature and wind speed and things like that, and then Geisha computes the evapotranspiration from that information.
But there is no way to import the evapotranspiration directly as a grid file.
As far as I know, I can't think of a way to do that. To just read your evapotranspiration as a grid file in. Maybe in the future there will be a way, but right now there's not a way. Yeah.
But in this situation, if we have this grid from the article from GIS or something like that, it will be distributed for change it by pixel by pixel. So we can have a evapor transformation different from this distribution.
So you're saying if you read the rainfall from ArcGIS,
Not into the other parameters.
the parameters. Yeah. So if you define your temperatures and wind speed and humidity, things like that, using ArcGIS, if you have those grids set up, then Geisha will compute the evapotranspiration with different values for each grid cell. And it uses the Penman method, or whichever method you select, but this is the method people usually use. Okay?
But you can't use more than one method for the whole grid. So if you
No.
have,
You mean more than one method of computing evapotranspiration?
so, for example, if you, as you show us, that you can have a polygon and say this is a wetland. So in this bucket, when you calculate the evapotranspiration for this area, it will will take the method for the whole catchment.
What are you asking? Sorry.
When you have a catchment,
Uh-huh.
and as you show us yesterday that you can have an area in this catchment and say this is define this as a wetland.
Uh-huh.
If we have to calculate the evapotranspiration for the whole catchment, we said that you will use a method like Penman method, for example.
Uh-huh.
This will be applied for the whole catchment.
The Penman method will be applied for the whole
for the
catchment.
catchment. And I can't say that this wetland will be calculated by other methods.
That's right. You cannot do that. So this is that's the time series editor. The time series editor allows you to prepare data for long-term data for using it in Geisha. And there are several options for reading in long-term data. I'm not going to talk about all these options. Once you read them in, you can view a time series of your data. Another one of the nice options in the time series editor is it allows you to there are different tools that allow you to interpolate your data to different time increments. So if you have daily data, you can interpolate that data to different time increments. And there are just a lot of different tools for interpolating your data in the time series editor. So and also you can format precipitation data. If you have precipitation data, you can convert that to the right format and save it as a Geisha precipitation file. So HMET, for HMET file, these are the data values that you need. So you need the date, hour, the barometric pressure, relative humidity, sky cover, wind speed, temperature, direct radiation, global radiation. Now if you don't have some of these values like the radiation values, then Geisha will compute the direct and global radiation using your latitude and longitude. It'll approximate those values and the time of year. So yeah, so you can format your HMET data using the time series editor. We've already talked about this. The formatted HMET data looks like this file. So these are all of your HMET values. This is your year, month, day, hour. This is so just all of those HMET values. So one of them is your wind speed, barometric pressure, temperature, radiation. After you've defined all that data, and you define your, so if I go back here to my Geisha model, go to your job control, define your long-term simulation parameters, so your latitude, longitude, and then your HMET data file, you define that file. You define the start and end times for your simulation. Then you can go ahead and run Geisha.
Excuse me, can I add maybe lat and long, or like many locations for this part? Or what is the lat and long you mentioned?
The latitude, longitude is used to approximate your radiation values, so your solar radiation
Okay,
values.
but if I'm talking about huge basin and giving just flat and lat and long, it may not be correct.
Yeah, if it's a really big one, it's a really big
Yeah,
basin.
we're talking about the night basin.
Yeah. So it does just take one latitude, longitude value.
So there is no option to add several lat and long, like many locations like the rain gauge, for example.
There's no option, but it's used to approximate. The only thing it's used for is to approximate your solar radiation. So if you want, you could define a grid of solar radiation values. I mean, it's not easy to do. And you'd have to compute the solar radiation for your grid, and then define that grid for each time in your HMET file. So you define a grid of HMET solar radiation files, several grids. For different times. So that's the only way to get different solar radiation values for different grid cells.
Excuse me, with ArcGIS, if you define project well for your catchment, ArcGIS can generate like a layer of solar radiation values. Is that yes? I think you can then export this new grid file into database.
Yeah.
Can I?
Yeah. So if you're using ArcGIS, you can create a grid file. Is that what you're saying?
For solar radiation. But I think it doesn't contain the panel. It gives one value for each risk. It doesn't ask at what day this solar radiation is on the block. Can search it.
Yes. So you'd have to save a separate grid for different times. You have to create a separate grid for different time steps.
But if
It's not easy to set up. Spatial.
Okay, if I have already these grids, how can I import it to WMS for a time series for the solar radiation, for example? For solar radiation would be read as well as you explained for the last two slides. Define the text file, which I will get the format from the wiki, the Geisha wiki.
Yeah, so you go to the Geisha wiki.
Solar radiation as a grid, and then I will upload it.
You just save it to some location, and you tell Geisha where the location is. So here in the long-term simulation parameters, it is define raster HMET files. And so you need to define a raster HMET file for your temperature, your humidity, your solar radiation values. So all these raster files. And you define a starting date and time, and an ending date and time. And then you're going to have a raster file for each time step. So normally maybe your time step is 1 hour. So every hour you'd have a separate ASCII grid file that gives your solar radiation values that cover your watershed. And the format, it's just on the wiki, on the Geisha wiki. So if I go to Geisha wiki, HMET raster files, we'll say. Well, might not be working. I don't know why. Okay. Go to Google. Google, maybe my internet is not working. I don't know why. Anyway, so if you just search for that, then on the Geisha wiki it's going to have the format, and it's it has recommended extensions for each file, so you have to have a temperature file and your radiation files and all that stuff. It has the formats. But it's not easy to set up, and WMS does not have an easy interface for setting that up. So you just define those files. You'd have to define them manually. So once you've done that, but if you don't want a separate value for each point in your watershed, you can just define a single HMET file using the time series editor. Once you've done that, define your long-term simulation in WMS, you can save and run your model. And so this is what your hydrograph might look like. You have flow versus time. And the other thing I wanted to talk about is boundary conditions. And so by boundary conditions, I am talking about there are different boundary conditions that you can set up in your Geisha model. So this is like if I have a hydrograph for like a large basin, and I want to input that hydrograph into a small area, and I want to figure out what the depths are in that small area. So I can kind of do a model for a small area with this. The default, when you run Geisha, by default, the cells on the outside of your watershed, there's no water coming into those cells. But you can define water coming into those cells, so flow rates going into individual cells. You can also define water depths for individual cells. And there are a couple of ways to do that. And these can be used to simulate, for example, if I have some flooding in an area, I could simulate a storm surge flooding. And you could do that. There are two kinds of boundary conditions in Geisha. One is called the overland flow boundary condition. If I define an overland flow boundary condition, like a water depth or a flow rate boundary condition on overland flow, then the cell where I define that overland flow boundary condition is where that flow rate enters the cell, or I can define several cells with the same depth, for example. And then Geisha will run with those values. You can also input a hydrograph from some other watershed, and so you have say I have hydrograph input at some locations in this model, and then Geisha will use that hydrograph to determine the flow depths and flow rates in a channel. So one of the things I want to talk about is there are three options for overbank flow in Geisha. And these options are defined in the let me show you where they're defined. So in the Geisha job control dialog, under this diffusive wave, that's my 1D hydraulic cross section. There are these options to allow for overbank flow and allow overland backwater flow. And so that's where you define these options. And let me talk about what those options are. So the default option, if I'm just running regular 1D channel routing, is in the default option this happens. So my I define my streams, and flow can go into my streams. So water can go from the overland flow into my streams, but water cannot leave my streams and go to the overland flow. That's the default in Geisha. There's another option that the same thing, water can go from the overland flow into my streams, but flow into the channel is restricted based on the depth of the overland flow. So in the first option, if the depth of the channel is higher than the overland flow depth, then flow still goes into the channel. In the overland backwater option, if the depth is higher than the overland flow depth in the channel, then flow does not go into the channel. And flow into the channel occurs if the depth in the channel is lower, but it's restricted based on the depth in the channel. So this is the overland flow depth. This is the channel depth. Water will go from the overland flow into the channel, but it's restricted based on the depth of the water in the channel. There's an overbank flow option, and that's so there's an overbank flow and an overland backwater option. In the overbank flow option, water from the channel can go onto the overland flow plane, and I can so if the water in the channel is higher than the overland flow depth, then the water will go onto the overland flow, and I'll be able to get flooding. I'll be able to see how much flooding happens on in my floodplain. So one of the problems, if you're doing a model that's completely based on boundary conditions and there's not very much precipitation happening, then you like for this model here, where I'm just doing the storm surge, for example, I might not be too concerned about precipitation. The precipitation doesn't have much effect on the flooding that's happening. Maybe I have big storm waves coming in, and the precipitation might not have very much effect. So I could either just define a very small amount of precipitation, or I can define my precipitation in the regular way. And a lot of times you won't have to define very much precipitation, but Geisha needs some value of precipitation to run, so you can't just define zero precipitation. You have to define some precipitation. And normally you could just use a very small amount, so like 0.01 millimeters of precipitation, and just use that. So this is, there's a workshop that you can go through that shows you how to use boundary conditions to figure out flooding. And this is for a hurricane that happened in the United States called Hurricane Ike. And it happened off the coast of Texas. This is Galveston, Texas. And so in the workshop you model the storm surge from this hurricane. It shows you how to do that. And there are different things you can view. Another part of the workshop is you can define a Geisha or an HMS model for if you have an area over here that's a large watershed and you want to model what happens if a storm happens in this watershed, what happens downstream from that storm. You can do that, and you just input a hydrograph somewhere on this stream, and WMS will figure out what kind of flood happens down in this area. And so that's another part of that workshop. So let me just I'll show you how to set up an overland or let me show you how to set up this kind of model. So, what's that? Oh, go ahead. So this is a model that I created, for the Sinai. If you remember yesterday, I think it was yesterday or the day before yesterday, we created this model. This is on the Sinai Peninsula. And so I can look at my maps here. Here's Sinai. And I brought in some elevation data and ran a HMS model. We also ran the Geisha model for this same area. And part of the HMS model is I got a hydrograph. So I went to this hydrograph, and this was my hydrograph. So if I want to, I can compute this hydrograph, and then I can input this hydrograph into WMS. Anyway, I created this model just downstream from this HMS model, just to see what would happen if I input this hydrograph downstream, and see what would happen downstream from this model if this hydrograph came through this area. And the way I set up this model, so I just created this grid. Maybe I'll show you here in a second how I created this grid, but created this grid, and then for this grid I created this Geisha coverage with this grid, and defined a flow rate from my HMS model. And the flow rate is just defined at my upstream node here on my stream. So at this upstream node, I defined this as a variable flow discharge stream BC type. Okay, that's stream boundary condition type. I define this variable flow discharge, and then I define this hydrograph. I got this hydrograph from HMS. So I went to HMS, you go to your time series table, and I just copy these values. So selected these values from the hydrograph, and then I copied them and then pasted these values into WMS in this window. Then I defined my my times, and the time increment for this HMS model was 10 minutes. So every 10 minutes I had a hydrograph value. So I copied that into WMS and defined that. The other thing that I needed to do was, for each stream that you want to simulate this overbank flow option, figure out what kind of flooding happens for each stream, you can turn this overbank flow option on. You could also just do it for your entire model. So I could go here to the Geisha job control and turn on overbank flow for my entire model. But if you have it defined for one of the streams, then you can't do it for your entire model because it's just defined for one of the streams. So I can either do it for the entire model, allow overbank flow, or I could do it for single streams. I did that, and then I ran Geisha, and Geisha ran, I got the depth from these flow rates. So if we just step through here, you can see that this, I get this water that comes down, and so I get some depth. Okay, and so just like any other model in WMS, or any other Geisha model that I create in WMS, I can export this to Google Earth if I want. So let's go ahead and export this to Google Earth.
Can I export it as a movie? Right?
Yeah.
Movie.
Well, it's a KMZ file.
Not only.
You want to export it as an AVI?
Exactly.
Yeah, so you can export it as an AVI or a KMZ or both. So the way I do that is I go to Data, Film Loop, and WMS is going to export both an AVI, so this AVI file, as well as a KMZ file. So let's go ahead and maybe I'll change some display options here really quick, and we'll try exporting it and just see how it looks. And I'll turn off my hydrographs. Then we'll go geesh to the data, film loop. We'll save these files. And so WMS is creating this movie file, and this will be saved to Geisha. Or to Google Earth, sorry. And it starts up Google Earth. I'm going to just change some of these settings, and we'll go ahead and play this. And it'll take a second for it to download the data, but once this finishes, we'll be able to see the flood depths in this area. So that's so we've talked about different rainfall methods, different long-term simulations in Geisha, and we've also talked about defining boundary conditions, so overland flow boundary conditions in Geisha. So there you go. There's our little map. So any questions about this stuff?
So for the urban simulation, or like the urban simulation you made, it was for Geisha, and for the hydrological model was for HMS. So you cannot combine both as Geisha, right? Or you can do it.
You could do both as Geisha, but the reason you would do a separate Geisha model, so you could do just one single Geisha model in WMS, and I mean you can only have one grid in WMS. And if I were to do a grid of this whole this area here, as well as the whole watershed that's associated with this area, then my grid cell size is going to have to be a lot bigger because it will take a long time to run. But with this model, I was able to make my grid cell size fairly small. So if I look at my cells, these are my cells. Whereas in the other model, my cell size was maybe 300 meters for my cell size. This cell size is maybe 50 meters for the cell size. So I get better resolution in this urban area. I could do a 50 meter cell size for my entire watershed, but I'm not going to get as good of the resolution for the depths and things is not going to be as good. So I don't know. Does that help?
Yeah. And just the last thing is related also for this part, for the urban flood part. You didn't delineate it from the digital elevation model, so you entered manually. Correct?
Yeah. So I could show you how I set up this model. Maybe I should do that.
Identify because here what I see is like you have one outlet or different outlets.
Yeah, I just have one outlet.
Yeah, that's why the water came, it's like spread it, but it's not like going at the end for the one outlet. It will not go directly to the sea. You know what I mean? Yeah. And this is a coastal area, so the water should not go into the outlet. Like several outlets. And it's
can we define the whole cells that at the sea as outlets?
So you would have to define, you can't define more than one outlet point, and you cannot in a Geisha model. You can only have one outlet. You can define additional streams and additional boundary condition points. So if what you can do is, if you know what the flow rate is going to be at different points in your watershed, you can find the different flow rates. So I could define, for example, I could define these as streams. And I could define the stream parameters. And then maybe I know that there's some flow coming into this stream, maybe at this location and at this location. I can define flow rates or water depths. If I know what the water depths are at those locations, I can define the water depths or flow rates at those locations. And so
usually these information are required, not the given data. The water depth and velocity at this shore area is what we need to know.
Yeah, so if you want to compute those, you would have to use something like HMS, do a separate model, separate HMS models for each of those locations, and then you would input it into Geisha here.
For the example you showed us about the hurricane at America, the water go to the land along maybe 1 or 2 kilometers over the shore.
Yeah.
So we have multiple inlets, and after the land be flooded, the whole amount of water come back again all over the same length of the shore. So we have multiple inlets and outlets. Isn't it the case?
Well, in that case, so the outlet location in that case doesn't really matter, because you're just defining what we knew what the water depths were along the shore. There are gauges along the shore that determine the water depths, and so we had the water depths, and you just enter the depths along the shoreline for that model for the hurricane.
As a time series value.
The time series, yeah. Time series of water depths.
So if you know the water depth at the shore, what you are trying to calculate, what is it?
You're just calculating where the flood happens. So what's flooded.
But I mean, if you know the depth, you can use ArcGIS to draw a layer with that depth to know what is covered and what is not.
Yeah, you could, or you could just use Geisha.
I mean, Geisha is a complicated mathematical calculation.
Okay.
But if you know the depth is 10 meters, just make a layer with 10 meters and everything under this elevation is covered. Anything above it is not. That's
Yeah, but it's not that simple. Because the water is different, has different depths at different locations. Okay, any other questions?
You say you're going to show us how to create this.
Yeah. So, what I did in this case, you can just use a map-based delineation. So, I'm just going to start from scratch here. So here's what I did. I have I'm just going to read in all my files that I have for this area. So I just created a DEM first. So here's my DEM. Here's the Sinai. Here's the area that I'm interested in modeling right here. You can also, so I have this other model for HMS that I could read in. So here's the HMS model. I could read that in. Oh, that's the Maud Clark. It's well, so this is my model area, and I want to do a model for the area downstream from this. I'm just going to delete this grid. So I have my drainage coverage. What I'm going to do first is create a new drainage coverage. So just create a new drainage coverage. And then you can just use the wizard, the hydrologic modeling wizard. So I already have my project data. I'm not going to worry about that, but I'll run Topaz. Sorry, I'm just getting really hot. No, it's okay. I just need to take this off. Hot. Okay, so I run Topaz, and Topaz gives me my flow accumulations, and then I can create an outlet point in this drainage coverage. And so maybe the outlet point I want is just on the, here where the ocean is. Create that outlet point. Then I can do this command in the drainage module, DEM streams to to stream arcs, DEM to stream arcs. And that'll, on my current drainage coverage, it'll create streams, so stream arcs. So I'm kind of doing a manual delineation, I guess a DEM based delineation. But then where this stream intersects this other model, so where it goes in, runs into this other model, and this other model starts at this location, I just break that stream. So I'm going to create a node, and then I'll delete this upstream segment. Okay, so I delete that segment. So I no longer have a stream there. And then I can also, if I want, I can define, if I want to capture maybe the flow that goes over into these areas, I can define some stream arcs along the shoreline. Just to, if I want to cover that area also. Or I could just leave it. And then these are stream arcs. Then I would delineate my basins. So I go to the drainage, define basins. So here's my basin. And then basins to polygons. And then I can compute my basin data. In this case, I'm just running Geisha. I don't need to get my areas and things for Geisha. Geisha already can get my areas. Okay, so here's my watershed boundary. Now what I did for this model is I just cut off this watershed boundary, and it depends on what you're doing, but to do that I just create an arc, start at the one end of this watershed boundary and create an arc along this boundary, and this is the boundary where we already have a watershed model. In this area I'd probably have to do a separate watershed model, but for this I just assumed that the flow was the same as the flow out of this watershed. So kind of manually defined my boundary. Then I deleted this section of the boundary, so this whole area here. And then I built my polygons. And so this is my model, my new model area, this polygon right here. Then I went back here to the wizard and selected my model, created a geisha model. I smoothed my stream arcs, so I went to this stream, selected, set my attributes, Manning's roughness value, and all these stream attributes, redistributed my vertices, smooth my streams. So here's my streams. They already don't have any adverse slopes, so I'm going to leave that. Then I created my grid, and I think I probably used like 100 meters for my grid cell size. And so this is my grid here. Then you define your starting and ending times for your simulation. I created a uniform index map, and that's just my land use type. If you have land use and soil types, different land use and soil types, you could do that. I just use a uniform, and then I use that and define my Manning's roughness values, so 0.1 or something for my Manning's roughness. Then I went to and defined my stream routing. We're not doing any infiltration. You could do infiltration in this model. And then you can just turn on this overbank flow option. Allow overbank flow. So you do that. Define your precipitation. You have to have some precipitation. I just used a really small amount, so 0.01. My duration was maybe 5 minutes, so just a very small amount of precipitation. And then what I did is at this upstream end of my stream, I defined a flow rate. So I went to the point attributes and selected a stream BC type variable flow discharge, and I went to here to HMS, copied the hydrograph and paste it into this model. And actually this hydrograph is in CFS, so I'd have to convert it to CMS, cubic meters per second. So you do that and you paste it in here. You define your times. The times are 10 minutes apart. And just define all of your times. You can do this in Excel also. So there's my times, there's my hydrograph. Call this input. and then you just run Geisha. Okay.
We look to define the round resolution as the output.
What's that?
At the end, at the output. Which round resolution will you define?
Which say that
Now
one.
you define the inlet at the outlet. It doesn't need any definitions before running.
So the outlet's just assuming there's you don't define it. It's just assuming there's no flow at the outlet when you start. And the water will go down the stream and you'll get flow at the outlet. But right now there's no flow. So when you first start, it's assuming no flow at the outlet. Just so the flow is defined here at this inlet point, and it just goes downstream to the outlet.
So this cell is the outlet point.
This cell would be the outlet cell. So that's how I did it.
By this way we get the floodplain.
Yeah, you get the floodplain. So that's, I don't know, are there any other questions about it? Okay. Alright, let's see where we are. The other thing I wanted to discuss, let's see, do we need to take a break? Should we take a break? What's that?
No, it's like have a break, have a You have Kit Kat in the Kit Kat.
Kit Kat.
You know Kit Kat? This what's the trick?
Oh, candy?
Candy.
Yeah.
We have this famous advertising. I'm afraid I'm a Kit Kat. Sorry. Sorry, but so
I don't know. I think your commercials here are different than the ones in the United States. So I don't think we have that slogan. Okay, let's have a break. Let's have a break till 9:30, and then we'll start up again. I just want to talk about reports after that. Reports. Doing reports. We'll have it. We'll talk about. I gotta talk about reports.
Excuse me. So flow starts from here and outlet. This is the outlet, and then the water covered this.
That's not saying that's what's actually going to happen.
هو قال لا يعرف اكثر من outlet. يعني الفكره انك تعرفي.
انا سالته اصلا هو عمل
لا دي ممكن
هاي 5 دقايق
بص هو فعلا انت بتشوف ايه الواقع اللي عندك وتحاول تحكيه بس كل اللي بيعمله ايه؟ ايوه بيتكلم
يعني هو حتى لو هو باللي هو قالوا عليه هو ما ينفعش.
We run the video.
You want to go to the video?
Yes. I mean the video of the flood, the last one.
بس محمل لي قناه صناعيه ان الميه تطلع فيه. هو ده اللي حصل عشان كده طلع.
الميه بترجع اصلا.
ايوه
بتنزل تخرج تحت وترجع على الارض.
يعني علميا
The one in Google Earth or the
the
AABI?
last one.
انا احط الميه ترجع لي او حاطط ايه؟
Exactly that one.
معلش الميه ما بتمشيش ستريم.
Of course, you know, now I want you to guide me. Maybe the Gisha is not the optimal case for my problem. You know, of course, you know that what I am looking for is the flash flood come from this region, go through here, and it go to the sea along this shore. Every meter along the shore is an outlet to the sea, you know. I think what is in this movie is it floods here and back to a point, isn't it? Is it running now? Okay. Where is the boost point? Okay. Now the water at this point will move. Where is the outlet? This one, huh?
This is the outlet.
So the water here does not, according to that simulation, does not move to the sea directly, but it returns back along this way till this point, then go to the sea, isn't it? This model assumes that. Look, look. Isn't it or not?
No, the water. So the water will go out to the sea. It just takes time for it to happen.
Yes, yes, I mean. Okay, now it started to spread. Could you pause it? Pause. Wonderful. Now the delta of the watershed has been flooded. That's great, and that is what is happening already. But what happens is the water go to the sea along the shore. You got my point?
Yeah.
So my question is, does this model assumes the water go out along this area or just recollect the whole water again to come out to the sea from this point only, as it is an open channel?
So it would go along this whole area.
Then
Water.
will this water return back to this point or go from here to the sea directly?
It would go directly to the sea.
Really?
It's just overland flow. If the overland flow takes the water out of the model, then it's just gonna go out of the model.
But indeed, after I saw that there is only one outlet is defined, which is here. It makes me assume that this water will not. The model cannot assume that this water will go to the sea.
Oh, it does. It's just overland flow.
Yes, after it is overland flow by the hydrographs that come from here. After ending this flood, that water has to go to somewhere.
So it just leaves the model.
It should leave the model from here. It should leave from everywhere.
That's what it does.
Really? If it is the case, if it flows all over the shore, so the hydrograph at this point must be very small compared to the one at the inlet, isn't it?
Yeah, it is.
So we can check.
Yeah, we can look at that. So let's read in.
استنوا احنا بنتناقش في this point. هنشيك على حاجة دلوقتي. ما احنا هنشوف. We will check now.
I can't remember where I saved it. Let's see.
هو مش في هي واقفة في الطابور مستنية التموين. عليكم السلام.
Here's the hydrograph.
Great. Now it is 120 meter cube per second. This is at the outlet.
1200, and then
And
in
the-
HMS, the peak was 5547 CFX.
Wow.
So it's a lot lower.
Could you check the total volume? Because the time could be spread. You got it? It may be reduced because of the spread, not because of
I mean,
the.
we could look at the Gisha report.
Yes. بسم الله الرحمن الرحيم. بسم الله الرحمن الرحيم.
So
Final volume.
final
Why is this?
volume on surface.
Why is this too? Is this at the outlet?
This is on the whole overland flow plan, the whole everywhere.
Yes.
Final volume on.
This one should equal to the input hydrograph, the volume of the input hydrograph from the HMS. Yeah.
This is the final though.
Total amount of the discharge, isn't it?
So the discharge.
Yesterday you showed us that we can define a single cell, and Gisha told us the hydrograph at this cell. You showed that yesterday to us. If we put one of these cells anywhere away from the outlet, it tells us directly if there is a water from this point to the sea or not, isn't it?
Say that one more time. Sorry.
Yesterday you told us that within Gisha you can define any pixel and Gisha gives you the hydrograph at this pixel.
Right. Yeah.
If it gives us a value of hydrograph far from the outlet, it means the water go out all over the shore.
Yeah. We could get the hydrograph.
I mean,
Anywhere.
yes, if this point give us a hydrograph, so it let the water go out from this point to the sea.
Yeah, so we could look at the hydrograph at that point. Oh, actually, so Gisha doesn't compute a flow rate hydrograph at each cell. It computes the depth at each cell. It doesn't compute
So
so we can look at the depth.
it will not show us.
There's the depth.
No, it will not show us the.
It's not the
It's
hydrograph.
important information, but it is not the one we are looking for. What we are looking for is the total hydrograph volume at the inlet and the outlet. If they are very far, so the water went out all over the shore. If they are close the same, so the whole water go out from a certain point.
So the hydrograph volume.
Volume, because you know that it takes longer time to spread and come back. That's why the peak had been reduced, not because
No,
different.
the volume
Okay, great.
is right here.
Okay.
795462994.
3 digits. I think it's about 80 million.
Yeah, 80 million.
Okay, it's 80 million
So I mean that's a,
at the outlet. 80 million.
and then the inlet. We could get. I think we can get that, so we can go. Yeah, I actually didn't compute the.
It should be calculated.
What I can do, I'd have to rerun the model. It takes 10 minutes to run, but I can
I mean the HMS results are there. We can check the total volume hydrogram. Isn't it? Can we?
I have HMS. I don't think it shows the hydrograph volume. It gives me the precipitation volume. I could compute it. I mean, I have this time series, so I have the flow rates. So the volume, you can compute it in Excel.
Cubic feet per second.
And I actually just copied this cubic feet per second, even though it should be cubic meters per second. So, Excel. So the volume is just
Cubic feet or cubic meter?
This is cubic feet, but
Okay.
that's what I entered into the cubic meter. I assumed it was cubic meters per second, so it's not correct, but I didn't convert it to cubic meters per second. So to compute the volume, you just go
I think you have to multiply it by 0.3 to the power of 3.
why?
Because 1 meter is 3 feet almost.
Yeah, but I didn't convert it. So I didn't convert from cubic feet to cubic meters per second. So 10 minutes. CFS. Seconds, I want cubic feet. So 10. So I have C cubic feet per second, and I'm going to want to convert that to cubic feet. So I have seconds per time step, and then I could do it. It's just
Google converts.
you do it.
Okay. Cubic feet per second. Okay. The time interval is 10 minutes.
Yeah, we need to start up again. Actually, so let's just not.
Yes, I had a call.
You can play around with it though. Just do it on your computer.